We'll move on to the next one, which is Huanqing Chen about recovering the density field inside the Quasar proximity zone at redshift 6. Please go ahead.
You see my screen and my cursor?
Yep.
Okay, cool. Yeah, thank you. I'd like to thank first to the organizers to give me this opportunity. I'm Huanqing Chen from University of Chicago. I work with Nick Nielin in simulating the quasar proximity zones at the end of cosmic reionization. And today I'd like to talk about my project of recovering density field using the Lyman-alpha absorption. The Lyman-alpha absorption spectra has been a powerful tool in probing the distant universe, especially at redshift 2 to 5. On the right, I show an example, a very nice spectra of redshift 3.6 quasar, and blue was of the Lyman-alpha emission line of the quasar. You can see numerous absorption created by the neutral hydrogen left in the universe. And by analyzing this so-called Lyman-alpha forest, we now know that IgM at redshift 3 is in a very ionized state. And also we can learn about the density fluctuation at that redshift and thus further constrain the cosmology. And on the astrophysical side, we can use them to measure the IgM temperature as well as the radiation background. However, at even higher redshift, the Lyman-alpha absorption is not a favorable tool to measure the IgM quantity, simply because at closer to the end of reionization, the radiation background is very low. Thus, there are too much neutral hydrogen in the universe that in most places they will cause this complete absorption. However, there is one place we can see the non-zero transmitted flux that is immediately close to the quasar, because the high ionizing flux from the quasar will further decrease the neutral fraction of the IgM. And this region, which we call the proximity zone, can extend up to dozens of comoving megaparsec. And with the high spectra now, which has the sub-Armstrong resolution, which is equivalent to 10 physical kiloparsec. That means that a lot of information is hidden here, and which we can potentially exploit to do a lot of science that we have done at lower redshift with the Lyman-alpha forest. And among the many IgM properties, the first one we want to study is the density field. And we studied them in simulation. So we start with a Croc simulation. It is a cosmological box with the adaptive refinement technique. We resolve the galaxies. And in the simulation, we include the relevant physics of gas heating and cooling, star formation, stellar feedback, as well as radiative transfer. And in the full simulation, the galaxies are the main reionization source, and the whole box reionizes at around redshift 7. So the 3D simulation doesn't include individual quasars. We do this by post-processing. We draw thousands of signs centered on massive halos, and then post-process them with a 1D RT code with a bright quasar spectra. So here is an example. From left to right are the radiation field, the neutral fraction of the IgM, and the transmitted flux. And we run the sign lines for 30 million years and then analyze the spectra. From this set of simulation, we gain some insights on the proximity zones. So the first one is that, very important point is that for the majority of the sign lines, the radiation profile is a very perfect power law with index -2. For example, in these typical sidelines, at first, the cosmological filaments may attenuate the radiation from the quasar by a bit, but because the brightness of the quasar, these kind of structures will be ionized in no time, to be completely transparent. And as you can see, like within thousands of years, the profile within the 4 physical megparsec from the quasar reaches a perfect r to the -2 power shape. And also the radiation field from the quasar is at least an order of magnitude larger than the ionization background created by the galaxies. And we should know that there are some sidelines that encounter the Lyman limit systems, but usually those Lyman limit systems will just truncate the proximity zone altogether. And inside the proximity zone, usually the radiation profile is also perfect r to the -2. And the second thing is that ionization equilibrium timescale inside the proximity zone is very short. So we can write down this equation. The gamma ionization rate we know is inversely proportional to r squared, and the alpha, the recombination rate, is only a weak function of temperature. So the number density of the neutral hydrogen, which is directly probed by the optical depth, is dictated mainly by the density of the gas. In a universe with uniform density, we know that the transmitted flux will be a very smooth shape like this dashed line, which I shall call the baseline. And with the density fluctuation, the transmitted flux will fluctuate significantly. And because we know gamma and alpha pretty well, to go back from the spectra to the density is also straightforward. We basically need to calculate the optical depth at each pixel and divide them by the baseline and take the square root. And the blue line here shows the recovered density field. And we can already see this looks pretty good. So let's take a closer look at this. There are several things I need to point out. First, because of the peculiar velocity of the gas, we can only recover the density field in the redshift space instead of the real space. So, which means we can recover the density as this black line. And because the quasar in the simulation is embedded in massive halos, which correlates to a overdensity field roughly equal to 1 physical megparsec. In the central region, there are some bias because the features are displaced by the significant inflow. While outside this region, we can see there are no such bias. But if we are further away from the quasar, the radiation field drops, so there are more saturated pixels. For example, here we cannot recover the density field. And in fact, if we assume that we can only measure the optical depth up to 5, then in this region above this dotted line, we can only place lower limit in the density field. And last point is that the thermal bordering will smooth the small scale spectra. So with this method, we want to naturally know how we can reconstruct the density probability distribution function, which is usually a very useful statistical tool. So here I show the true density field calculated directly from the simulation and smoothed by a Gaussian kernel of 25 kilometers per second. As we expected, in the central region, because the massive halos correlates with the overdensity, this inner region has a systematic, more dense PDF than the rest, while outside of this region, the PDF looks very similar. And the recovered density field here plotted in the dotted line, we can see that except for the inner region, which is suspect to the bias by the systematic inflow related to the quasar, the rest of the PDF agree very well with the true one. And here is the truncation is because of the saturation farther away from the quasar. And in summary, hopefully I persuaded you that with the high resolution spectra we can now obtain, it is time to look into the proximity zoom in detail. And with this method I just described, we can measure the density field in proximity zoom at redshift 6. And this method is sensitive to density fluctuation around the mean with moderate scatter. And the recovered density PDF agree very well with the true PDF at a distance larger than 1 physical megparsec. And the last point I want to mention is that now that we know we constrain the cosmology quite well, so we can model the true density PDF very well. And by comparing the recovered density PDF to the true, we can constrain more quantities of the quasar itself. For example, their intrinsic spectra and their environment and age and so on. And thank you very much. And I'd like to take questions.
All right, so we have some time for questions. The first question is, do you include in fact of helium reionization? Heating due to helium plus may systematic influence everything?
We included, and the result I show here is the result for quasar lighting for 30 million years. So, which means that the helium front propagate throughout the outside of the 4 physical megparsec. So, which means that this heating effect affect all the pixels here. And in fact, if this the position of the helium front will also impact the density PDF, which is potentially useful to help to using the PDF. We can constrain the quasar age.
Thank you. I have a quick question. In your recovery, you assume that you know exactly what the ionization flux for the quasar is, and also the background, outside background, UV background. Is that right?
So definitely, I assume that we know the luminosity of the quasar, and I think this is a quantity directly observable, and I assume that this the quasar luminosity stay the same during the whole time, and the background is drawn from the simulation, and this will vary by a few factor of a few, but this will always be lower than the quasar radiation by roughly an order of magnitude. So the background radiation is not as important.
All right, thank you. If people have more questions, we can continue those on Slack.